Hi, in today's video, I'll be talking about asymptotes and limits. So first, we're going to talk about what are asymptotes, what are limits, finding the vertical asymptotes using limits, finding horizontal asymptotes using limits, finding oblique slant asymptotes using limits, and a special case, crossing horizontal asymptotes. And finally, an important point. So first, what are asymptotes? An asymptote is a line that a graph approaches but never touches as the input value x approaches a specific value or becomes extremely large or small. Its purpose is to describe the end behaviors or behaviors when approaching the undefined points. There's many types of asymptotes, including vertical ones, horizontal ones, and oblique ones. Now, what are limits? A limit describes the value of a function approaches as the input x approaches a specific value. Its purpose is to analyze the behavior near a point, not necessarily at that point. Its notation is written like this. So first, lim is for limit, and as x approaches a, the function gets closer to m. So now we're going to talk about finding vertical asymptotes using limits. So the definition here is a vertical line x equals a is a vertical asymptote if the function approaches infinity or negative infinity as x approaches a. So, for example, the limit connection we have here is as x approaches a from the right, the function approaches infinity. As x approaches a from the left, the function approaches minus infinity. So the steps to find if there's a function, if there's a limit, is to first find where the function is undefined. For example, find a division by 0. Then evaluate the limit of the function as x approaches these points. If the limit goes to infinity or minus infinity, then a vertical asymptote exists. Now, for example, we have an inverse function here. So function equals 1 over x minus 5. So this has a vertical asymptote of x equals 5. But how do we find that out? First, find where the function is undefined. So for example here, division by 0. To create a division by 0 here, x would have to equal 5. So now we have a place where the function is undefined. Now we have to evaluate the limit of the function as x approaches these points. So for example, take x equals 5.1. When x equals 5.1, the function equals 1 over 5.1 minus 5, which is 1 over 0.5, 0.1, which is 10. Now imagine if x was 5.01, then the function would equal 1 over 5.01 minus 5, which is 1 over 0.01, which is 100. So as we get closer to 5, as x gets closer to 5, y gets closer to infinity. So now, for example, take x equals 5.001. Then the function would equal 1 over 0.001, which is 1000. So now the limit, theoretically, as x approaches 5, would get closer to infinity. So now we can assume the function has a vertical asymptote at x equals 5, since the limit goes to infinity as x approaches 5. Now we're going to talk about finding horizontal asymptotes using limits. So first, a horizontal line y equals m is a horizontal asymptote if limit approaching a constant as x approaches infinity, positive or negative. So first, here the limit connection is as x approaches infinity, the function approaches m. As x approaches minus infinity, the function also approaches m. But when x approaches infinity, the function approaches m from the top, while when x approaches minus infinity, the function approaches infinite bottom. So now the steps to evaluate it is to first evaluate the limit of the function as x approaches infinity or minus infinity. If the limit approaches a finite value, then a horizontal asymptote exists. So first you have to replace x with the many numbers to really find out if there's a horizontal asymptote or not. Now, so for some general rules, when the degree of the denominator is smaller than the degree of the numerator, y equals 0. When the degrees are equal, we have to look at the leading coefficients, and if the degree of the numerator is bigger than the degree of the denominator, there's no horizontal asymptote. So basically, here it tells us to evaluate the limit of the function as x approaches infinity or minus infinity. We have an example here of an inverse function. It's already told that the horizontal asymptote is at y equals 3, but we're here to prove it. So first replace x by take 10. When x equals 10, we get 30 over 10 plus 2, so 12. 30 over 12 gives us 2.5. Note 2.5. Now take x equals 100. Now we get 300 over 102, and that gives us 2.94. So we're getting closer to something. If we replace x by 1,000, we get 3,000 over 1,002, which gives us around 2.99. So it's clear we're getting closer to 3, right? But to prove it even more, you can look at these formulas, not formulas, rules, but formulas too, right? So now here, because the degree of the top, so the numerator, is 1, and the degree of the denominator is also 1, degrees are equal, which means we're going to have to look at the leading coefficients. Now the coefficients here are 3 and 1. 3 over 1 gives us 3, which means the horizontal asymptote is at y equals 3. So now we're going to talk about finding oblique, so slant asymptotes using limits. So here the definition is a slant or an oblique asymptote occurs when the graph of a function approaches a line as x approaches infinity or minus infinity. It occurs when the degree of the numerator is 1 greater than the denominator. So here, the limit connection here is as x approaches positive or negative infinity, the function minus a linear function equals 0. So now first the steps to find this are to evaluate the limit of the functions as x approaches infinity or minus infinity. If the limit approaches a line that is neither vertical nor horizontal, then an oblique asymptote exists. Then you could perform the polynomial division to extract a linear term. The quotient, ignoring the remainder, will give the equation of the oblique asymptote. So here, for example, we have a function, x squared plus x plus 1. So now here we can see the degree of the numerator is 1 greater than the degree of the denominator. So here the degree of the numerator is 2, while the degree of the denominator is 1. Then there's two options. First, you could use this option right here, which is to add minus 4 and plus 4, right, to cancel out the denominators. Or you could just divide both polynomials and it could still work. But for example, take this right here. So now we subtracted 4, so we're gonna have to add 4 back. Now because we get x squared minus 4, that is also equal to x plus 2, x minus 2. Now we can cancel out the x plus 2's, which gives us x minus 2 plus the right side which hasn't been cancelled, x over x plus 2. Right. So now the quotient, ignoring the remainder, will give the equation of the oblique asymptote. The quotient here was x plus 2, so x plus 2 is the oblique asymptote. The remainder, 4, is only going to be useful to determine how close the function is to its asymptotes and not necessarily the asymptotes asymptotes themselves. So now we have a special case, a crossing horizontal asymptote. The definition here is a crossing horizontal asymptote occurs when the graph of a function intersects its horizontal asymptote at one or more points. The explanation here is a function may cross a horizontal asymptote, for example, certain rational functions. It seems counterintuitive since asymptotes are often thought of to be approaching but never touching. An example here is take the function x over x squared plus 5. The degree of the numerator is 1, but the degree of the denominator is 2, which means technically y should be equal to 0. But for y to be equal to 0, x also has to be equal to 0, which means the function's crossing the 0, 0 point. So basically what that proves is there's special cases where the function could cross the horizontal asymptote one or more times, but it never crosses the vertical asymptote. But now I have an important point. Take, for example, this question. Function of x is equal to x squared minus 16 over x minus 4. Is x equals 4 an asymptote? I previously said that for x equals 4 to be an asymptote, we had to find an undefined value, right? And here, the undefined value would be dividing by 0, which would make sense with the x equals 4. But the answer here is no. But why is it no? First, take a look at this function. X squared minus 16 over x minus 4 can also be written as x plus 4 times x minus 4 over x minus 4, where the x minus 4's can cancel out, which leaves us with function of x is equal to x plus 4. That proves that there's no horizontal asymptote. Also, that can be written also as x gets closer to 4, the function gets closer to something. If you calculate it, for example, replace the x by 4.1, for example. Here, if we replace the x's in both the numerator and the denominator by 4.1, we get that the answer here is 8.1. If we replace it by 4.01, for example, to get closer to the original x equals 4, even though x can't be equal to 4 because we can't divide by 0. So if you replace x by x.01, for example, we'd get 8.01. So realize now that as we get closer to 4, we aren't getting close to any infinite, but we're getting closer to 8, which doesn't make sense because for vertical asymptotes, you need to get closer to infinite as x gets closer to a certain number. So x cannot be a vertical asymptote. X equals 4 is not an asymptote, but instead there's a hole at the point 4, 8.